Thank you. Thanks for the invitation to come speak. It's really a pleasure to be here. I'd like to talk about descending cohomology geometrically, and by that I mean I'd like to consider the question of when the cohomology of a projective variety over the rationals can be modeled by the cohomology of an abelian variety. And this is motivated by a question that Barry Mazur asked at Joe Harris's conference, and so I want to give some affirmative answers to that question in two cases. One case where we put some restrictions on the Chow zero group, and the other in the case of fibrations and quadrics, and showing essentially that Beauville's arguments give you another case, another answer to Mazur's question. All right, so let me just start by mentioning Mazur's question. So let's suppose X is a smooth projective threefold over Q, and H30 is equal to 0. So does there exist an abelian variety, say J over the rationals, such that there's an isomorphism H1 of J Q bar, QL coefficients, to H3 X Q bar, QL coefficients twisted by 1. So given such a threefold, can we find this abelian variety over Q that models the cohomology of the threefold? Yes, yeah, as in this isomorphism as Galois representations, not just that the dimensions of the vector spaces are the same. So there are certainly answers to this question in the literature, and I'll mention those, at least some of those in a second. But let me just start by putting some bullet points up here that motivate this question. So the first bullet point is motivation is from number theory. And I'll expand on these in a second. But there's theorems of Deligne, Mazur, and Tate-Honda that suggest that the answer may be yes. And I'll explain that a little bit more detail in a second. The second motivation is from complex geometry. And then let me say in this setting, there's some work of Deligne, Muir, and Bloch-Srinivas, and Voisin. Essentially, some of this is through algebraic cycles that gives some motivation for the question in this perspective. And I'm sort of arbitrarily breaking up complex geometry and algebraic geometry. But there's also motivation from algebraic geometry coming from the work of Clemens-Griffiths, Mumford, and Beauville. That I'll also explain. So the second two approaches are the ones that I'm going to speak the most about. But let me start by explaining a little bit of why Mazur thought that such a thing might this abelian variety might exist, and he's calling these phantom abelian varieties. And I think the motivation for that name will be clear in a second. So the motivation from number theory, I think, can be summarized best as saying that some obstructions that you might think exist potentially to preclude, something that might preclude the existence of this J over Q, those obstructions, quote unquote, vanish. So let me explain what I mean by that. So you could try So a theorem of Deligne would tell you that you could try to preclude the existence of J over Q by showing that the eigenvalues of the characteristic polynomial of geometric Frobenius are not divisible by P for infinitely many primes P. Unfortunately, this doesn't preclude, or fortunately or unfortunately, this doesn't tell you much because the theorem of Mazur, this is the so-called Newton over Hodge theorem, tells you that if you assume that H30 is 0, like we're doing, then these eigenvalues are divisible by P. So this potential approach to an obstruction is not going to give you an obstruction. That's one bit of motivation. As well, the theorem of Tate and Honda tells you, so because you know this information about the eigenvalues of geometric Frobenius, of the characteristic polynomial of geometric Frobenius, the roots of the eigenvalues or the roots of the characteristic polynomial. Because you know this information, you know that there exists, so for infinitely many primes P, there exists an abelian variety over FP bar that gives you an isomorphism H1 of J FP bar, so and this is actually over P, FP, J FP bar QL to H1 of X FP bar QL of 1. Thank you, H3. In other words, over infinitely many primes, there is an abelian variety over FP that gives you, that would be the reduction of the phantom abelian variety mod P if it were to exist. So somehow the picture is we spread out over Z, and over infinitely many primes we have an abelian variety, and we want to know, can we fill it in over Q? Yeah, well, the way that I'm getting this is I'm saying that I know that the eigenvalues of Frobenius are divisible by P, and then those collection of numbers tell you by Tate Honda that there is an abelian variety over FP that has those eigenvalues. And then that tells you the representations are the same. Right. Yes. Yeah, I mean, if there was a Tate Honda for number fields, then we'd be. Yeah, exactly. Okay, and so I think that this is some motivation for calling these phantom abelian varieties. This is sort of the phantom that exists over, that should exist over Q, but we can't quite see it yet. Okay. Okay. All right, so let's look at some motivation from complex geometry. Okay, so here we're assuming that H30 is equal to 0. So this tells us that the intermediate Jacobian J3 of X. So let me pull back over the complex numbers, and there'll be a lot of subscripts because I'm trying to keep track of which field. I'm always starting over Q and then pulling things around, and I'll just put some subscripts to kind of keep track of that. So if I look at XC and I look at the intermediate Jacobian, this is going to be H21 of XC, sorry, 1, 2, modulo H3 of XZ, and this turns out, to be, in this case, the algebraic intermediate Jacobian, so to speak, which is algebraic. So this is algebraic. And we can ask, does J3 of xc descend to an abelian variety J over Q such that there's this isomorphism H1 of JQ bar QL to H3 XQ XQ bar QL. All right, and I want to generalize this slightly because some of the results that I'll state and they're in the literature are a little bit more general, but they generalize the question in two different ways, two obvious ways, and I just want to emphasize the difference between those two generalizations. So let's let X be just any smooth projective variety over Q, so I don't restrict to threefolds. And let's assume one of two things. Either we just look at H3, we assume that this is level 1, or instead let's give this dimension m. Sorry, let's have this dimension 2n plus 3. And I'm choosing that kind of funny notation so that the numbers come out better later when I'm doing quadric bundles. And let's look in the middle cohomology. And let's ask that this have level 1. Yeah, and yeah, sorry, n is an integer. Yeah, I want to look in the odd groups. And oh, actually, no, in this, actually, no, you know, yeah, this really, I should just put this here. I'm allowing any dimension, but I'm just looking at H3. Yeah, and then in the second one, I'm looking in the middle, and I want the odd. Yeah, and then for dimension 3, these two things would coincide. Okay, and then we're in the similar situation where we now have the intermediate Jacobian. So J3 and J2n plus 3 are algebraic. And we could ask, you know, do they descend to Q and give, I'm just going to say for short, a phantom abelian variety. So I'm just generalizing this question in these two different ways, two different pieces of the Hodge structure. And I'm going to talk mostly in the start about number 1. So I allow any dimension, but I focus only on the third cohomology. But before I do that, I want to mention some motivation from part 2, and then later I'll also switch to part 2 instead. So motivating this line of inquiry, let me just mention a theorem of Deligne. If X is a complete intersection, with these hypotheses, then there is a phantom abelian variety. For 2. Okay, so I mean, this is going to work in a lot of cases, and you know, let's try to. Yes. Yes. You should get it. Yeah. Let me come back to that question also, because there's a point where I was wondering something along. So I'm going to eventually assume that Chow zero is put on a curve, and then go through an argument. And there's sort of one place where, somehow just having an Abel-Jacobi map surjective is almost enough to get everything that I want, except for sort of one part. And maybe there's another way to get around it, and then you could just have the Hodge conjecture, and it would be enough to get the general case. Maybe. So then I can ask you, then maybe see if. Okay. Okay, so before coming back to this question here, I want to just motivate again in one more way this question. Looking at Mumford's algebraic construction of the intermediate Jacobian of a cubic threefold. And this is related, to another construction that is also related to this question, looking at Albanese's of Fano varieties of lines, but I'm not going to take that approach here. And that would be the work of Clemens and Griffiths, which motivates another line of inquiry of this problem. But I'm looking at sort of Mumford's take via prims. So this is the algebraic construction of intermediate Jacobian of a cubic threefold. So X is a smooth cubic hypersurface sitting inside of P4 over K, where K is some algebraically closed field. The idea is you pick a general line, and project away from that line. And so you then look at the blow-up along this line L of X. And this has a map to P2 K. So the picture is something like I've got my cubic threefold X, and I pick a general line. I project away from that line. And the general, so if I pick a point and I get a point of, so the target is P2. If I pick a general point, I get a fiber which is a residual conic to that line. And there's going to be a discriminant curve that I'll call delta. And over delta, I'll get singular conics. And in the way that we set this up with the general line, we get that over a point of the discriminant, there's exactly two lines. And if we take the Stein factorization, so from the relative Fano variety of lines in this blow-up over P2K, then this gives us a map to an étale double cover that I'll call pi. So this is a P1, has P1 fibers, and I get a double cover of the discriminant curve. And if we take the prim variety, then over C, we get the intermediate Jacobian back. And in addition, over any field, we're going to have that there's an isomorphism, any algebraically closed field, H1 of the prim. QL coefficients are isomorphic to H3 of X twisted by 1. Okay. So we get something very close. And recently, Jeff Achter showed that if x is defined over q, then you could pull back to q bar, you get all of this stuff. Then this prim variety descends to q, and so you get another. So this case of the cubic hypersurface is already dealt with by Deligne's theorem, but this gives you another approach to that case. So this prim would be the phantom abelian variety. And so this points to two approaches more generally. So let me just mention Beauville's generalization. The same. So for any k algebraically closed, the same holds up to Achter's statement. Same holds for fibrations and quadrics over P2. Sort of two approaches that this suggests you might want to do. One, you might want to show that you can do the same thing and descend everything over Q. In the case where you already knew that this conic bundle was defined over Q. Or two, you might just want to go through and check that Beauville's construction holds over an arbitrary base, and then you would just get the same result. And so, I mean, so that this prim construction holds. So characteristic not equal to 2 everywhere throughout the talk, essentially. Holds over, arbitrary bases. Okay, so not surprisingly, that works. So essentially, I want to also explain, that this construction works. Okay, so before I come back to this question of fibrations and quadrics, I want to make these seem like less independent results and put them into kind of a framework. And to do that, let me talk about the main result. Okay, so the first thing I want to talk about is giving an answer to Mazur's question if Chow 0 is supported on a curve. So let me put up a theorem. And before I do this, let me first say that Jeff and I owe a great deal to Claire Voisin, who suggested how this question is related to some work of Muir and Bloch-Srinivas, and suggested sort of an approach to the problem. And this is essentially a report on our success in implementing that suggestion. And we thank her again for his suggestions. So this is the theorem. So let's let X be a smooth projective variety over the rationals. And let's see, let's assume that Chow 0 of X, we pull back the complex numbers, is supported on a curve. And I'll explain that in a second. Then I'll just say, let me put it this way, then, then there exists an abelian variety J over Q, the phantom abelian variety, such that there's this isomorphism H1 of J Q bar QL maps isomorphically to H3 of X Q bar QL twisted by 1. So we're answering this sort of this first generalization of Mazur's question. in particular H300, I'll explain this in 1 second. I wasn't able to do it, but maybe as we go through, you'll see. I mean, I should say that some of these lines of inquiry are pretty new to me. So this was the approach that I was able to see, but maybe there could be other places, and I'll mention where that question comes up. Okay, so let me make some remarks. So first, what does it mean for Chow 0 to be supported on a subvariety? So Chow 0 of xc supported on a possibly reducible subvariety V means that Chow 0 of xc minus V is equal to 0. So in other words, from the exact sequence, from this inclusion, you're saying that Chow of V surjects onto Chow of x. All right, then there's a standard result by now, a generalization of Mumford's theorem that says that if Chow 0 of xc is supported on a variety of dimension d, then hi 0 of x is equal to 0 for I greater than the dimension of d. Okay. So in particular, in this case, H30 has to be 0. Also, H20 has to be 0, which is maybe not optimal. So this is not, there are plenty of cases that this theorem wouldn't hold, but if we could change this to a surface, then of course this would be a stronger statement. And then I should mention that the Bloch-Beilinson conjecture implies that the converse holds. So if you have the vanishing of these cohomology groups, then you can say something about the support of Chow 0. And so let me just say, in other words, what I'm saying is that conjecturally, this theorem should apply anytime that H20 is not, H20 is equal to 0. So any threefold with H20 equal to 0 should, if you believe these conjectures, be handled by this theorem. Okay, and then just to keep in mind, that if you're rationally connected, that would be an example where this would hold. So in particular, all Fano varieties would be covered. So not just complete intersection Fano varieties like in Deline's theorem, but any Fano threefold would be covered. And in addition, this is another kind of obvious statement, but I just want to put into context the case of quadric fibrations and quadrics. If we look at, suppose that X had a morphism to some variety S, if the dimension in every fiber is rationally connected, if the dimension, so a surjective map, the dimension of S is equal to 0 or 1, so if the fibers are either X when you're rationally connected or rationally connected surfaces, then this theorem applies. Okay? But on the other hand, if you have a surface and the fibers are rational curves, if the surface does not have Chow 0 supported on a curve, then this guy won't either, and that would be an example where our theorem would not apply. Okay, so I'll come back to that later when we talk about fibrations and quadrics, but that's the connection between the two cases. Okay. So let me now describe the proof of the theorem, and that'll also cover a little bit of the background for this statement. So So the first things to look at are results of Muir. So let me start with those. And let me just review what it means to be an algebraic representative of AI. So I'm going to use the standard. So X is going to be a projective, smooth projective variety over an algebraically closed field for now. And I'm going to look at the Chow groups of X. And sitting inside of these Chow groups are these groups of cycles that are algebraically equivalent to 0. In other words, I'm using the standard notation and not Fulton's A's. These are the algebraically equivalent to 0 A's. What does it mean to have a regular morphism from one of these AIs into an abelian variety? So A should be an abelian variety. And I can look at maps on K points that are homomorphisms of groups. And to be regular means that for any smooth variety, so smooth pointed variety, T, and any relative codimension I cycle parameterized by T, well, I'm going to get a map. So I get a map from T to AI of X to A. Let's call this phi. And I'm going to call this WZ. And the map WZ is just the obvious thing. You just take Z at T, and you subtract off Z at your T0, where T0 is the based point of this space. So it's clearly algebraically equivalent to 0. T is connected. So this is clearly algebraically equivalent to 0. And then you can consider this composition of set maps. And you can ask whether that's the induced map from an actual morphism of varieties from T to A, because they're both varieties. If that always happens, then you call this a regular morphism. OK, so then you can ask for such an abelian variety that's initial amongst all of these abelian varieties admitting morphisms from AI. And that's initial. So an abelian variety that is initial. As above, so let me just draw the diagram. In other words, I'll use the notation, we have AI of X, and we're given some map phi I sub X to what I'm going to use the notation ab I of X for algebraic representative. So given any regular morphism from AI to X, there's a unique morphism making this diagram commute. Okay, so that's what it means to have an algebraic representative of AI. Okay, so for example, A1 of X has as its algebraic representative. This doesn't have to be an isomorphism, but in these cases, it will be. Pick 0 of X, and if D is the dimension, then AD of X would be isomorphic to the Albanese of X. So in those two cases, algebraic representatives. Thank you. Thanks. Thank you. Yeah. Thanks. OK, but in general, there may not be an algebraic representative. So I want to put up a sort of remarkable theorem, to me, remarkable of Muir, that says for codimension 2 cycles, there's also an algebraic representative. So under these hypotheses, there exists an algebraic representative ab2 of x, phi2 of x, and if L is not equal to the characteristic of the field, then we get a map from H1 of ab2 of x with QL coefficients into H3 of x with QL, H3 of x with QL coefficients twisted by 1. So it's sort of this remarkable statement. There exists an algebraic representative, and its cohomology behaves like you would expect. Okay. Say again? Smooth projective variety. Yes. Yeah, I mean, I didn't say an isomorphism, but just an inclusion. That's sort of going to be the heart of the matter and some dissent. And I'll put up the second part of his theorem in a moment. Let me just say, just put up two claims that are going to sort of do everything for us now, and we'll focus on those two claims. So what we'd really like to know is, in the case now we have x over q, we'd like to know, does ab2 of x q bar descend to some j over q? So that's claim 1. And then claim 2, the dimension of H1 of x q bar is equal to the dimension of H3 of x q bar QL. Okay, so this kind of reduces the problem to just descending this algebraic representative and then checking a dimension count. Yes. Yeah. Sorry. Yeah. So H30. Sorry. I'm going to put always Chow 0 of xc supported on a curve. But so far I don't really need if I could get. I mean, clearly that won't hold in general. But if I do something like H3 0 was 0, then this would sort of be a plausible statement. We could just hope that this would just work there. That this is. I'll definitely get at the level of complex numbers, but then there's a question that I can ask later. I mean, I was wondering this. Maybe that it's straightforward, and that would be great. So over C, yeah. Okay, even over. Okay, great. That would be great. Okay. All right. So let me now describe these two pieces. So the first is just, I'll just state as a proposition, which is that this descent works. So let me just put up the statement. K is a perfect field. So that's capital K. And then little k is the algebraic closure of big K. Let's take x big K, a smooth projective variety over big K. And then let's put x to be the pullback. If AI has an algebraic representative, abi of x, then abi of x descends to capital K, and won't write out the whole proof, but it's just what you think. There's a universal property of abi. So what we need to do is we need to lift the action of the Galois group of the field up to K. You just use the universal property, and of course this is going to work. So use the universal property of the algebraic representative to lift the action of the Galois group of K over K to ab I of x. And that does it. No. Yeah. I don't even need that I just think that this exists. I don't even need anything special about its construction. It's just the universal property that I'm using. So if it exists, I'm saying it's going to descend. So this means that I want to focus on this dimension count. Okay, and I'd like to first put up a theorem of Muir that I think gives some motivation for how to proceed. So this is the second part of Muir's theorem. If you look over C, so under the same hypothesis, then ab2 of x is the image of the Abel-Jacobi map. So I've got A2 of x, and this maps surjectively onto ab2 of x, which sits inside of J3 of x. So if we knew that the Abel-Jacobi map were surjective, then we would be all set, at least at the level of complex numbers. And for that, well, definitely the Hodge conjecture alone would just give that under our hypotheses. But let me break this down a little bit more. So this sort of suggests two subclaims. So this is that the Abel-Jacobi map from A2 of xc ab2 of so to J3 of xc is surjective. And claim 2.2 would be that just the dimension count, the dimension of ab2 of xc is equal to the dimension of ab2 of xq bar. And in fact, we'll get equality on the nose. But so if I pull this back to C, so this is a statement, I'll ask again to the audience, actually. I mean, to me, this seemed like a very strange, I just assumed this was going to be true, that there's going to be equality here. I'm taking an abelian, my algebraic representative over q bar. I pull it back to C. How much different can it actually be from this guy here? Under these hypotheses that we're going to use, they're going to be the same. There's an easy argument, but maybe there's something more general that would just give this. Okay, so let me focus on these claims, and it leads us to the work of Bloch and Srinivas. And to this theme of the decomposition of the diagonal. So let me just put up their theorem, or kind of a slight generalization of what's actually stated in their paper, but is well known. So let me put it this way. X is a smooth projective variety over an algebraically closed field, as usual. And I'm going to put characteristic equal to 0, or you can assume a resolution of singularities for things showing up in the statement. If Chow 0 of x omega is supported on a curve, okay, omega for some universal domain, omega containing q, containing k. So this is just omega is algebraically closed, and the transcendence degree over k of omega is infinite. That's what it means to be a universal domain. So suppose that, for example, the complex numbers containing q bar is the case we're going to use. So suppose you know that Chow 0 is supported on a curve when you pull back to some universal domain. Then you get a bunch of statements about the algebraic representative. So 1, a2 of x to ab2 of x, the map from Muir is an isomorphism. 2, the same thing holds when we pull back x to omega. Okay, and then if we assume that k is equal to complex numbers and that Chow 0 of xc is supported on a curve, then I'm going to put Voisin's name here because I learned about how this works from these arguments from Voisin's papers and talks. It says, although I think sometimes she's attributed this as part of this theorem, but the statement is then 1, this map ab2 of x is an isomorphism. So you don't really need to pull back to universal domain for C. And then on top of that, you also get that the Abel-Jacobi map is also an isomorphism. Okay, so and what the arguments really come down to the fact that if you assume that Chow 0 is supported on a curve for this universal domain, then you get a decomposition of the diagonal over k. And then you use that to, these decompositions of the diagonals give you all of these statements. That's kind of the heart of the matter. So this pretty much settles. So assuming that we have Chow 0 supported on a curve, we get a lot of mileage. So so for us, when we're back in the situation of x over q, we have that ab2 of xc is isomorphic to j3 of xc. And this gives us claim 2.1, that the Abel-Jacobi map is surjective. So what we really just need to check now is the dimension count. All right, so all right, let me make some remarks. So in order to get this surjectivity of the Abel-Jacobi map, we could have instead of using this Chow 0 supported on a curve, we could use some other hypotheses like the dimension is 3 and we're uniruled, or H3 is 0, H3 0 is 0, and the Hodge conjecture. Those will all work to get at least this statement here. And so the statement that I want to focus on is then checking is making this dimension count here. So although it seems strange, a priori, I don't see why when I pull this algebraic representative back to C, it has to be this algebraic representative here. But there's a hypothesis I can make that it makes it easy, but maybe it holds a more generality, and then the theorem would hold more generally. Okay, so 3.4, I'll call this algebraically closed base change for algebraic representatives. Put the statement there. Okay, so the lemma is the following. So let's have omega over k be an extension of algebraically closed fields, not necessarily a universal domain, but just some base change by an algebraically closed field. X a smooth projective variety. And if I assume, which we'll have in this case, that I of x mapping to ab I of x is an isomorphism, and also that ai of x omega, mapping to ab I of x omega, is an isomorphism, then, and let me just, you don't need characteristic 0, but just to make sure that it's, this statement holds, then these two things are isomorphic. They're always isogenous, but then ab I of x pulled back by omega is isomorphic to ab I of x omega. Okay, so I'm asserting that under these added hypotheses, I could definitely get this. Maybe there's a better argument, but in this case, it's the statement is, well, it's sort of easy. You look at n torsion. You know how there's a theorem of Leconte on pulling back cycles by n torsion. You get isomorphism. This sort of forces everything to be isomorphic on n torsion, and then you get the isogeny and the characteristic 0. You get an isomorphism. So, proof. Look at n torsion, and then proceed. Okay. So that completes the proof. And let me just make a couple of remarks. Which it seems that these remarks should be expanded on, but let me remark what I know, and then. Okay, so what we're saying is that we showed the following. So assume x is a smooth projective variety over Q. Let's assume one of the following things: hi 0 is equal to 0 for I greater than 1, and Bloch-Beilinson. Or dimension of x is equal to 3. X is uniruled. And ab2 of xc is equal to ab2 of xq bar pulled back to c. Or 3, that h30 is equal to 0. We have this statement here, ab2 of xc equals ab2 of xq bar pulled back by c in the Hodge conjecture. And we really only need this for x times j3 of x. So if you have the Hodge conjecture for that particular variety, then the phantom abelian variety exists. So some possible other hypotheses we could use to get this result. And so, of course, the point that I'm making, it seems like it's possible that if we could just get rid of these hypotheses here, it'd be a much nicer statement. Okay. All right. So so that completes the story for the first result. Any questions? Yeah. Okay. What I was confused about was that somehow, what if, like in this case, it just happened that it was a point, and then here it was much bigger, is ab I. And so I pull back, and somehow I just have a point, and everything sort of commutes in the diagram. But then but that was for a fine. Okay, yeah, no, I really believe that is. Yeah. Okay, and then it should hold. Okay, yeah, that. And it may be that. Yeah, this holds in more. Thank you. Yeah. Thanks. I also thought maybe of using maybe symmetric products and trying to argue like for Pick and the Albanese or something. That seemed less likely to work, just because you may not have surjectivity. But thanks. So I don't know if I'm supposed to end before the hour or on the hour. Okay, I'll just do another 5 minutes then. So what I'll do is I think just from this result, just explain where the statement for fibrations and quadrics comes into play as part of this picture, and then I'll just state the result, and then we'll end there. That shouldn't take too long. Okay, so how does this fit in? I want to sort of phrase this result again in this way I mentioned before. Well, let's imagine that we have our threefold, and we have a map from our threefold to some variety. I mean, I want to think of the maximally rationally connected fibration. Is kind of what I want to think, but think of it as a morphism. And I want to ask that all fibers are rationally connected. Okay, then the theorem certainly holds if S is a point or S is a curve. Then we have Chow zero supported on a curve, and we're done. So let's consider the case. So the next case is is S is a surface, and maybe the surface has Chow zero not supported on a curve to make it more interesting. Okay, and then let me also make so every fiber. We have a surface, we have a fibration. So to speak, every fiber is a rational curve, but that could be a very bad fibration. Let's make this even easier, so simplify it even more. Let's assume that there is a degree D, and every fiber, geometric or not, is so every fiber, let's say x ks, sits inside of p d ks with Hilbert polynomial dt plus 1. Let's make this really easy, just to try to get an extra case or two out of this. And let's take d equals 1. Okay, then I get just a projective bundle because of my hypotheses. Then everything is easy. You just use the Leray spectral sequence, and you're done immediately. And there is a phantom abelian variety. So the next case is d equals 2, and then already I think that this is interesting. So the statement would be, so let me just put sort of, let me paraphrase, and we'll end with this. So the Mumford Beauville approach holds with mild hypotheses on the surface S. So their construction was for S equals P2. You can generalize that a little bit. So mild hypotheses on S holds, and the phantom abelian variety exists. That's the result that I was going to talk about if we had more time, is how to set that up. So let me just point out that it seems that, for instance, if we could get rid of this hypothesis, then this would deal with these uniruled cases all in one fell swoop. This would be sort of a concrete way of giving some other examples through the geometry. Okay, so let me stop here. Thank you.